Greetings. In this talk, I will discuss FRBs and the low twist model. This model was motivated before the radio burst associated with the Magnetar short burst from SGR 1935 or the discovery of long-term periodicity in FRB 180916. This work involves Andrei Timokhin, Paz Benyami, Cecilia Scirinti, and others. Below are some papers associated with this work, and I encourage viewers to read them. I also have an associated poster which highlights some of the work. So this model was motivated by what we noticed was a striking similarity of arrival time statistics between an episode of FRB 121102 shown on the left, observed by GBT, and Magnetar short burst episodes, one of which is shown on the right. And you can see the similarity in the arrival times between the two. This behavior is epitomized by the unusual logged uniform burst rate, something that is rare in astrophysics and is seen in earthquakes and solar flares. And this was also noticed by Tabor and Loeb. Magnetar short bursts are continuous fireballs at very low altitude, as well known from spectroscopic studies. And more recently, we have shown periodic windowing or phase selection of Magnetar short bursts, shown on the right here, in SGR 1830. This implies a very low altitude for Magnetar short bursts and the putative trigger associated with FRBs. And so the cartoon picture is some sort of dislocation event or oscillation at very low altitudes near the Magnetar. So what is the low twist model? In a nutshell, it is the Timokhin's errant mechanism for radio emission. And this requires very low charge density, aka low twist, and a strong magnetic field for non-stationary single photon magnetic cascades. The energy scale between FRBs and typical radio emission, the vast energy scale difference, is basically explained by the different trigger. Here it is crustal oscillations, dislocations on a larger surface area at a higher frequency associated with the crustal oscillations and dislocations in a higher magnetic field. And this can readily explain the energy scale difference. Moreover, the universal power law of -1.7, which is well known in the Magnetar community, can be interpreted as a Poynting flux scaling, which may be mapped to the event size distribution of FRBs. This mapping suggests the voltage scaling of FRBs, similar to what is seen in pulsars. This also implies the efficiency of FRB radio emissions is not fixed, but is higher at lower energies. We can also generate luminosity functions from the scaling with some simplistic assumptions and parameter choices. See my paper here. The low charge density condition also implies ultra-long period magnetars may overproduce radio emission compared to more normal spin period magnetars. They ought to be rare with different possible production channels. See this paper, Benyami, Wadiasingh, and Metziger. Note that the burst from SGR 1935 agrees with the predictions of the model. Moreover, the radio preceding the spikes in the X-rays is also what you'd expect from avalanche pair cascades, which then eventually Comptonize. Interestingly, QPO structure was seen by the HMX team associated with the two radio spikes. In a recent radio paper with Cecilia Scirinti, I consider these radio train or spikes or trains as FRB trains as a method to constrain the neutron star equation of state. Different lines here are different models for the equation of state in the core and the crust. Note that for extragalactic FRBs, you have to correct for the redshift. Systematics in clusters or islands of such waiting times or QPOs will blur the distinction between these eigenmodes. However, the low L eigenmode should be more easily distinguishable by future large samples of these FRB trains or QPOs. I will end my talk by leaving up these model predictions. I encourage you to pursue and peruse the papers, and I welcome any comments. Thank you.